Welcome to The Explainer. Today, we are diving into a concept that's, well, fundamental to literally everything that spins. We're talking planets, we're talking figure skaters, even the wheels on your car. We are talking about the moment of inertia.
So just picture this for a second. You've got a figure skater pulling in their arms and suddenly spinning like a top. You've got a planet just hanging out in orbit. And then you have a simple wheel just rolling down the street. I mean, they seem totally different, right? But they all share this deep fundamental secret.
And that secret is they all have this built-in resistance to being spun. You can almost think of it as a kind of rotational laziness that every single object has. And it's this laziness that decides exactly how they're going to act when you try to make them rotate.
Now, this rotational laziness actually has a name. We call it the moment of inertia, and we usually just write it as the letter I. And here's the best way to get it. You know how mass is an object's resistance to being pushed in a straight line? Well, moment of inertia is the exact same thing, but for being twisted or spun. It really is basically rotational mass.
And this comparison just makes it so clear. We all learn in basic physics that a force makes something accelerate, and its mass fights back, right? Well, in the spinny world of rotation, a torque, which is just a fancy word for a twisting force, is what causes rotational acceleration. And what fights back? The moment of inertia. You see, the parallel is just perfect.
So, what is it that actually determines this rotational laziness in an object? Well, that brings us to our first really big idea. It's all about where the mass matters the most.
And here it is, the key insight. For moment of inertia, it's not just about how heavy something is. Nope. What's way, way more important is where that mass is located compared to the point it's spinning around.
Okay, check out this classic example, a ring and a solid disk. Let's say they weigh the exact same amount and they're the same size. For the ring, all of its mass is packed as far away from the center as it can get. This gives it a really high moment of inertia, which makes it tough to get spinning. But the solid disk, its mass is spread out all the way from the middle to the edge. And that one simple change in where the mass is gives it a much, much lower moment of inertia. It's way easier to rotate.
And the reason why comes down to this one simple but super powerful formula. To find I, you add up every little bit of mass m times its distance r from the center squared. And that r squared part, that's the secret sauce. It means a piece of mass that's twice as far from the center has 4 times the impact on its rotational laziness. That's why distribution is everything.
All right, so now that we know how to measure rotational laziness, let's connect it to what actually makes things spin in the first place. What we can kind of call the rotational force.
Come on, everybody knows Newton's famous F equals ma. Force equals mass times acceleration. Well, guess what? Rotation has its very own version. Here, torque, that's the Greek letter tau, equals the moment of inertia, I, times the angular acceleration, alpha. The relationship is exactly the same. Give it more torque, you get more spin. But if you have a higher moment of inertia, you're going to need a lot more torque to get the same result.
Okay, now this is where moment of inertia gets really, really cool, because it unlocks this powerful conservation law, and it explains what I like to call the skater's secret.
We've all seen this, right? A skater starts spinning, kind of slow, arms out wide. And then, just by pulling their arms in, they accelerate into this incredible blur. How do they do that? They're not pushing off the ice again. So where's all that extra speed coming from?
The answer is hiding in one of the most powerful laws in all of physics, the conservation of angular momentum. Now, angular momentum, L, is just the spinny version of regular momentum. You calculate it by taking the moment of inertia, I, and multiplying it by the spin speed, omega. And the law is simple. If nothing from the outside is twisting the system, its total angular momentum has to stay constant. Period.
So let's break down the magic. Step 1, the skater's arms are out. This puts their mass far from their center, giving them a high moment of inertia. And at that moment, their spin speed is pretty low. Step 2, they pull their arms in tight. By bringing all that mass close to their axis of rotation, they dramatically lower their moment of inertia. And here's the punchline. Because that total angular momentum has to stay the same, and their I just went way down, their spin speed, omega, has no choice but to shoot way up to make up for it. That's the secret. No extra push, just physics.
All right, let's take this same idea and apply it to another classic physics showdown, the Great Rolling Race. It's a downhill battle that's all about mass distribution.
So here's the setup. You've got a solid sphere and a hollow one. They weigh the same, they're the same size. You put them both at the top of a ramp and you let them go. Which one makes it to the bottom first? What do you think?
Well, the winner is decided before the race even begins, by their moment of inertia. The solid sphere's I is 2/5 mr squared. The hollow one, with all its mass on the outside, its I is 2/3 mr squared. Now, since 2/3 is a bigger number than 2/5, the hollow sphere has the higher moment of inertia. It's the lazier of the two racers when it comes to spinning. So, why does the less lazy one win? Well, when these things roll, their energy gets split into two jobs, moving forward down the ramp and spinning. The hollow sphere, with its higher I, puts up more of a fight against spinning, so a bigger chunk of its energy has to be spent just getting it to rotate, which leaves less energy for actually moving forward. The solid sphere? It's the opposite. It's easier to spin, so more of its energy can go into pure forward speed.
And that's why the solid sphere wins, because it's less rotationally lazy. More of its energy is free to become forward motion. This gives it a greater acceleration down the incline. It'll get to the bottom first every single time, and it's all because of how its mass is spread out.
You know, this all comes back to a really core idea. Moment of inertia isn't some fixed property like an object's weight. It absolutely depends on the axis you choose to spin it around. As one of our sources puts it so well, changing the axis changes I. It's a dynamic thing that depends on both the object and how you decide to spin it.
And this principle is just everywhere. It's in the design of high-tech flywheels that store energy. And it's even at the very heart of how giant clouds of gas and dust collapse to form those incredible spiral galaxies we see deep in space. So the question I'll leave you with is this. Where else do you see this fundamental rotational laziness quietly shaping our entire universe?